we are looking at trajectories. And we were looking at trajectories that had some properties to them: an initial height, an initial angle, and an initial velocity. And what we're interested in doing is a bunch of very pragmatic calculations of, hey, where do I land when I start with these things? Or if I have a target, how can I choose my angle or my launch speed to land at that particular point? All of those can be turned, all those goals can be turned into nonlinear equations. I want to set things up so that certain things are equal. My landing x value is equal to something. All right. We fortunately found two categories of nonlinear equations, one which was nice, or nicer. Linear is the best. Linear is the bestest equation we could have in the whole wide world. But if we had to pick a second best nonlinear, it would be polynomials. They have really nice structure to them. And we actually found that there's a command in Matlab that'll pretty much handle any polynomial you throw at it, up to like ridiculous 80 degrees. It'll, x to the 80, it'll handle that fine. What we were facing with at the end of last class, though, was something that was not so nice, something that actually didn't have that clean a solution. So we'll take a look at that. So last class, the final thing was experimenting with launch angles to land at a certain target, to land at 30 meters out. And we actually did a pretty good job by guessing and checking, right? Another thing that we could consider doing is looping. This is a favorite of students because you know how to loop, and so it becomes really easy to try this. But basically do a for loop on your angle, launch things, and then see where you landed. It's not, I'm going to advise you against this, and we'll see why as we go through this, this week. Not the best approach for a whole bunch of reasons, so let's think about why one approach might be better than another before we get right into the coding. So considering our long-term goals and our evaluation, our metrics, how are we going to be happy with one method and unhappy with another? Efficiency is going to be a big thing. I'm going to talk about this at a very macro level today. If I was doing this for my job or for something else, we're going to focus in on some particular things of efficiency as we go through this. But honestly, this is the kind of algebra or calculation I go through when I'm faced with a new problem. I ask myself, all right, it's going to take me some time to code up anything, right? I'm going to have to think about this code. There's going to be bugs. I'm going to have to write it. How much code am I going to have to write? That is something to factor in if you're trying to get a project done in a certain amount of time, or just as fast as possible. That being said, there's often a trade-off. There's the program, once it runs, how quickly is it going to spit out an answer? If I shave some corners and do some hacky code, but it makes the computer code really inefficient, like say solving those huge matrices, if I did that wrong or used the wrong approach, then I saved myself 5 minutes of coding, but it took the computer 2 more days to do the actual calculations. Maybe that's not the best trade-off. So there's something about well-designed code and how much time you want to spend there versus the product you get and how fast it's going to run on your particular problem. And there's a final trade-off, which is that's great, but how good is my final answer? Is it super accurate or not so much? So what we're going to do is start off with some code and use the metrics we just talked about here. How fast is it for me to code up? How fast does the program find an answer, and how accurate is it? And we're going to try that with loops first off. So over to Matlab. All right. So this is a paraphrasing of what we had last week. I'm just going to run it once. And what we get is a plot of the one trajectory. You can take a look at the top of the code here and just remind you of all the pieces that we built up last class. We have an initial height. We have an initial velocity. We pick an angle in degrees. Notice there's cos d, tan d down here. Those are the cos and tan functions in Matlab that take degrees as input instead of our favorite friends, radians. Basically, we've got this roots command further down. This is the calculation side here. Once I have the velocity and the height and the angle, we created mathematically on paper a polynomial that told us, okay, the parabola we get is going to have x's in it, and I want to find where the x gives us y equals 0, and that's what those 2 lines there did. They built a polynomial, the coefficients of it, p, and then we used the roots command to find out where the impact point was. The problem with this impact point is that's not where we want it to be. Today we've changed our target. Our target is now going to be 35 meters away from the end of the track, or from the start of the track. We're landing currently at 30. So we might want to change our angle a bit, and we've experimented with this last time. We could literally just cut and paste and try 68 degrees, run that. Oh, that's getting closer, so how about 70 degrees? Oh, sorry, wrong way. 65 degrees. That's a little closer. But as soon as we start doing manual things like that, it feels a bit awkward, it feels a bit of a pain. So the other thing we can do is try to put a loop around this. Here you have to be careful about where you're going to build things. To me, G is a constant, that's fine. Everything else down here is stuff that changes dependent on my angle. All this stuff down here depends on my angle. So I'm tempted to put a for loop here. So for theta naught equals, let's go from 45 up to 85 degrees, say. And what that'll do is take out the need for this first line. So we're just going to have that loop over 45 degrees up to about 85, probably in there somewhere. We'll go to the end, put an N down here. Then my favorite two keystrokes, Control A, select all, Control I, indent everything. And then I can see what all is in the loop. There's my entire loop. And what should happen then is we'll choose the angle, then we'll draw a graph, that's fine, we'll plot stuff, we'll calculate the impact point, that's the most important thing for us. And yeah, let's just try this and see what happens. Spiffy, all right. That's actually kind of cool. Maybe not really what I wanted, but you can actually see what happened if you zoom in around this region. Cool. So what we did is just planned all those different trajectories with different angles. And some of them, 35's in there. You know, one of them in there is pretty close to 35 at a landing point. I can't really spot it on the graph very easily, so I might look to my output and go, oh, sorry. Some things hit around 33, 33, okay, 34.5, 35.3. There's an angle in there that's pretty close. I would need to tweak my code, though, to be able to make this useful. What would be a nice next step? Okay, so if the impact is within a range of 35, so I can set my target and say if I'm plus or minus 1. All right, so what we could do is add an if statement to this at the end here. All right, so why don't we do it this way? We'll do a little if statement. If x impact is less than 36, say. Actually, let me do this the old-fashioned way. Spelled impact right is the first start. Is greater than 34. So within 1 degree. Notice, and I'll try this in a second, then we'll do a print statement, fprintf, angle. This is where it's nice to have the print statements. Angle is some angle, and the impact x is another thing here. Our angle was theta 0, and our x impact is x impact. All right. So notice there's two little print statements, %.1f here, one here. The theta one goes to the first one. The x impact goes to the second one. So we'll see both outputs as we go. If it's less than 36 and bigger than 34, print stuff out. Huh, lovely. All right. So we find out that at 62 degrees and 63 degrees, we're in the right ballpark. Sorry, so improvements. This is great, but it's not that accurate an answer. So one of the things is accuracy. How can I tweak my accuracy here? Yeah.
You can change your increment of your theta naught.
Absolutely. Change the increment of our theta naught. So this is default counting by ones. Yep.
Put it in the if statement so that you only have to do that increment for something actually near your value.
Okay. So there's two things we can do. So let me try the simple, naive way, which is to increment this. And then you're right. There's something about the if statement we might be able to take advantage of as well. All right. So let's go by 0.1s here and just see what happens. Okay, then we see a collection of graphs, which is awesome. And we also see, there we go. Let me just increase our accuracy a little bit here so we can see that we're not actually landing exactly at 35, but we're getting close. Oops, I think I took out my slash in, %f. So I'm just going to add a few more digits on the where did we land part. There we go. There we go. So we're landing at 35, 1 centimeter past, 2 centimeters past 35. Pretty good. And the angle we would use for that is 62.4 degrees. Excellent. So can you paraphrase your suggestion about the if statement and how you would tweak the if statement?
If you put the increased, like the smaller increment in the if statement, and you're only doing it for that, actually near the angle instead of having that many.
Excellent. Okay, now I got it. So you could do 2 loops. You could have this one count by ones, and then have inside your loop down here, once you know you're close, you could count by 0.1s and then zoom in on that. Absolutely. These are all completely reasonable ideas. What I feel when I see those, though, is there's a trade-off. I'm having to think a lot about the mechanics here, about, okay, where am I doing my loop? I've got another loop down here. I'm tracking where am I changing theta? Is it going the right way? Maybe I need to go back by 0.1s if I've gone too far. There's a whole bunch of user thought there that I think we can avoid. It's doable. This is not, it's not the worst way to do things, but it's, as we'll see, there are lots of better ways to do it. So we're going to explore those. What I'd like to capture, though, is that idea of, okay, let's go by 0.1s and then zoom in once we know we're close. That idea we can use and hopefully apply more effectively and more simply, rather than having a series of finer and finer loops, which is kind of where we're headed with this. I would also like you to notice the accuracy. Even if we did that kind of for loop and zoomed in a bit and had by 0.1 degrees and 0.001, it's a lot of work to get every little extra digit of accuracy. And it doesn't feel that smooth or that easy to code up. So just keep that in mind. With loops, we can get down to 1 degree, 0.1 degrees pretty easily. Past there, it'd be a lot more either computer runtime as it searches all these very, very small angles, or a lot more us time to build up the loops very carefully.